The presumed difficulty of coordinate reference systems is related to something which you may have been able to see behind my head on previous occasions. It's a globe. Now, the spatial conundrum is that we have to deal with handling something as perhaps beautiful but awkward as a globe. And a globe, we can define positional information on the globe, and I referred yesterday to the book which I was given when I was 10, which explained, for instance, this picture here shows how one might divide up, like dividing up the parts of an orange, dividing up the globe into points of reference. Dividing up the globe into points of reference. So this is something which for me has been innate, obvious, something I haven't bothered to consider since I was a child. Consequently, figures like these showing the way in which the globe can be represented as a grid on a sphere of degrees cast from the assumed center of the Earth outwards. This has been second nature. However, representing spherical coordinates as degrees is not necessarily second nature, and the problems of having to handle or having to represent spatial data in this way are manifold. So I now try to share my screen once again and hope that I don't have to back out of it for too long. So I'll try and find out whether okay, so recording is running, so we should be back where we were. This appears to be the same problem that I was facing yesterday with, and I don't think that my machine has gone back to running Wayland. No, so it's running X11. And this, I'm not running Wayland, but it's still misbehaving. So I'll attempt to first open up the document, and then I'll try to share the screen, and we'll see whether it would be okay. So I should be able to move up and down in this, but beyond that, I'm not quite sure what it will let me do. And I'm not sure whether it will let me stop sharing either. Okay, so coordinate reference systems are a requirement of spatial data. We could say that we would like to have 3D coordinates, so both depth and a position on the sphere. And indeed, the systems used by GPS or satellite navigation systems do assume a position in three-dimensional space, that the network of like a tent, the network of satellites around the Earth works in three-dimensional space rather than in a spherical geometry, so that they work in a standard representation, partly attenuated by the known relative or the signals are attenuated by the relative resistance shown by the atmosphere. Up until space travel, then all we have known about the representation of the Earth, for instance, as on a globe, and spherical representations of the Earth have been known or existed for a long time, back to prehistory. But how to work with spherical representations has only been understood in more detail over the last 1200 years or so. Other civilizations before that had some understanding of the way in which one needed to step back from planar geometry. So that quite a lot of the difficulties involved in coordinate reference systems are concerned with advancing understandings and techniques for handling how to get from how we know how to handle planar geometries and representing space or two-dimensional space as a planar geometry, but in fact we're actually dealing with, in the case, for instance, of Google's S2 library, in a spherical two-dimensional space. So that's the surface of a sphere. Coordinate reference systems are essential to tell us how the coordinates that we've recorded are specified. We could say, okay, they're defined in decimal degrees, but decimal degrees could begin anywhere on the Earth, so that the zero could be we could rotate the globe and put the zero lines for longitude and latitude anywhere. By convention, the zero latitude line has been taken for a long time to be the equator, even though we know that the globe, the tilting of the globe changes through in an annual cycle, so that we go from now we're entering the northern hemisphere winter, but the southern hemisphere is entering summer. So we could conceptualize this in a number of ways. Latitude, okay, zero goes through the equator. We also have to have some idea of where the equator is, and typically we know where the equator is because that is where on the equinoctials, so it's the time at which we're in between the winter and summer seasons in both hemispheres, when the sun is vertical at the equator. As we move into the summer, the verticality of the sun shifts in the northern hemisphere, shifts northwards until the 21st of June, and then back again. So that we're in a fairly complicated setting, but the equator, we think we know where the equator is, and certainly navigators have had some reasonable idea of where the equator is for quite a long time. Degrees of longitude are more complicated and have only really been grasped since the invention of clocks or timepieces, which could be transported and which would survive journeys at sea. On land, finding degrees of longitude is a little easier because you're trying to work out when the sun is highest, and in particular when the sun is highest either at the equinoctials or in particular at the summer and winter solstices, so that it's possible to work something out without having satellites out there. And surveyors and very often military engineers have made an extremely good job of trying to establish where everything is without access to being able to view the globe from outside, from a satellite. However, this leads to considerable complications in the representation of spatial data. And spatial data has typically been surveyed or it's been needed by jurisdictions, often military jurisdictions, over time. Now, the software which has been being used for quite a long time, certainly since the 1990s, is the Proj library. And the Proj library first was built around the need to project and inverse project from a known sphere to a choice of different projections. And some of these could be Mercators, the transverse Mercator, the universal transverse Mercator, or UTM, Lambert equal-area. There are a number of different mathematical models for how to move, particularly for chosen parts of the surface of the Earth, from a segment of a sphere to a planar representation. If you get the relationship wrong, you can work on the map you have, but when you wish to add other information in a different projection, then you have to know the relationship between the source and target projections in order to combine them. So that, for instance, using the R-Gödel library, and the same kind of thing is available from SF, you can ask the external Proj library, what does it know about the definitions of the ellipsoid? Now, my globe appears to be spherical, but in fact, the Earth is an ellipsoid, and measurements by surveyors without having access to satellite measurements made a series of estimates of the major and minor axes, so that when major is represented as a distance in meters from the assumed center of the Earth, and where B is given, that's the distance in meters in the other direction. So this is across the equator, and this is from pole to pole. Or you can have a relative flattening coefficient, which is around 300, but it's a relative flattening coefficient. And as you can see, the Proj library knows about quite a number of these definitions. Area and modified area are used in the United Kingdom. This is an Australian measurement. This is the 1967 representation, which was a geodetic representation, quite widely accepted worldwide. This one was used a lot in North America, the Clark 66. This is 1866, slightly modified by Clark in 1880, and again a French version of this one. And these are Everest 1830, 1848, 1856, and so on. So that there were a number of different definitions used in parts of India. This is the international. This was an international conference at the end of the 19th century, and so on. So that we start by 1960 to get to the World Geodetic System. The World Geodetic System started developing by communication between the national mapping agencies, where the desire was to establish some international norm for the major axis and the relative flattening of the poles. So you get the World Geodetic System of 1960, 66, 72, and then you get to 1984. 1984 was about as good as it could get at that stage for a group for a compromise between national mapping agencies to find something that more or less worked for everybody, and which seemed to match the observations being made from satellites. So that from satellites, it was possible to build instruments which could measure distances very accurately, extremely accurately. so that one could get down to sub centimeter and sub millimeter distances. As here we're dealing in meters, so you could say, okay, so we're good for about a meter, and this is about what the ellipsoid looked like in 1984. It's a compromise, and unfortunately, these are the full names of these systems. So that if we go down here, then we get to the World Geodetic System at the bottom, and finally the normal sphere, which is used in web mapping, which doesn't take account of the fact that the ellipsoid is an ellipsoid. Other parameters which one might wish to add to a description of the globe are where the prime meridian is. So one often says that it could be Greenwich, which is where the longitude 0 is present. But in many situations, the prime meridian is not Greenwich. Certainly in older maps, then this was usually taken as some description for a given mapping agency. In the case of Norway, it's a stone at the back of the office of the mapping agency in downtown Oslo, which you can go and look at. However, knowing the ellipsoid is not quite enough, because not only is the ellipsoid not regular, but also as time has gone on, one has understood more of the relative placing of the tectonic plates on the surface of the Earth, so that national mapping agencies or regional mapping agencies have also developed a system which is known as DATUM. This is a book, Datums and Map Projections by Iliff and Lott. And the importance of datums, probably the difference from ignoring the datum is going to be of the order of 150 meters plus minus 150 meters. And for many purposes, this was not considered important. Each national mapping agency had its own 0 point in terms of the ellipsoid assumes that the globe has a smooth surface. However, the relative smoothness depends on the relative density of the mantle. That's in vertical terms, how far we are from the putative center of the globe doesn't only depend on the shape of the ellipsoid, because the further north you go, you're a bit closer to the putative center of the Earth. But if the mantle is denser or heavier, then you will be in a depression on the ellipsoid. Everybody knows that if you look at if you touch your skull, you'll find some bits which are a little bit higher. It's not a completely round entity, and in the same way the globe is not, so that there are parts of the globe which are a little bit depressed and parts of the globe which are a little bit extended in relation to the smooth geometry of the ellipsoid, which we've sort of looked at already. In addition, parts of the globe move upwards or downwards dynamically. In Scandinavia, one talks about isostasis, and this was caused by the extra weight of the ice sheets 10,000 years ago or more. And since they melted, much of Scandinavia has been rising, in some cases as much as a meter every 100 years. So that's a centimeter a year. In other parts of the world, the depression is also dynamic, it's continuing. So that this has nothing to do with sea level changing, but it's that the actual shape of the underlying geologies influence where we are in relation to the ellipsoid. And what the datum is trying to do is saying, okay, so that we need to fix this so that we know we arbitrarily take a given point and say what the distance to the assumed center of the Earth is. Now, surveyors had to make an assumption about this, and very often they would take a point as the mean sea level and put a brass plate there and say, okay, this is the datum. And in the case of the stone in Oslo, there are two marks giving the height above mean sea level on two particular dates. So that one was an earlier date, and then it's corrected to say that this is actually a couple of centimeters higher than what we thought it was. And this is then the vertical datum in relation to the assumed center of the Earth. Now, before satellites, we didn't know where the center of the Earth was, but now we have satellites, we know where the center of the Earth is. So the datum matters. And in WGS 84, a compromise was reached on how to establish that datum. Now, if you make a different assumption about where the datum is, you get different decimal degree coordinates coming out, because everything is being slightly shifted. One talks about datum shift, slightly shifted in relation to the nominal ellipsoid, which is smooth, so that as you're moving things around, then they move on that surface. In addition to that, there are horizontal shifts because of the fact that the tectonic plates themselves are moving. So when I was asking yesterday about earthquakes, then earthquakes are part of the picture, that the tectonic plates are moving in 3 dimensions, and each time they move a given coordinate, say that you have a centimeter correct decimal degree coordinate, the item or object to which it's referring will not be in the same place in relation to a fixed 3D geometry, because the underlying body has moved, assuming that the Earth was standing still. The Earth's actually going round quite fast and then going around the sun as well. But assuming that we were looking at a fixed body, then because of the tectonic shifts, then things would have moved as well. So that many of the coordinates that we handle would really need to be specified. When you, in temporal terms, you could talk about the time zone, but in geodetic terms, then you need to talk about the datum. And the datum also needs to be authorized. Somebody needs to say, well, it's not just something we found out. Now, when we started using the Proj library, we picked up the changes which had been made to the Proj library by those who had extended its implementation. One of the things which had been done was to add a datum definition for a known list of datums. However, this list was never properly authorized. And the second step which was made, so that so I say the datum tag supported a partially informal list of values. This was somewhat complex, and these were then linked to lists of 3 or 7 coefficient datum transformation sets. That's to make assuming that we're not looking at time-specific coefficients, so that you could, in 3 dimensions, you could say, okay, to get from datum A to datum B, we need to shift the X by this number of meters, the Y by this number of meters, and the Z by this number of meters. So that's the 3 coefficient set. And then the 7 coefficient added further details to the if you like, the first derivatives of those. So we're looking at the changes, and you got 7 coefficients. Typically 3 coefficients were the ones with the major changes, typically around 125, 150 meters for the X and Ys. Sometimes the X was more than the Y more than the X, and things like that. And that they would be known as the 2WGS84. So for any for any datum, it would tell you how to get to the WGS84 definition. Now, in the 1990s, 1984 was yesterday. It was very recent. And being very recent, what one needed to do was to bring historical data, which say could be from the 1930s or the 1910s. In North America, one used the North American datum of 1927. One needed to bring them to WGS 84 or GRS 80, or a modern representation of the global datum. But 1984 is now 36 years ago. And so we began to realize that we needed to change our approach to handling coordinate reference systems. One of the really interesting sources of information for those who have an engineering or technical bent are the grids and datums column in photogrammetric engineering and remote sensing by Cliff Mounier, who describes in a he writes very engagingly. The anecdote, which I'm not even sure if I remember it correctly, but it was that he said, okay, so that for the Danish Mapping Agency, they have standards for Denmark, but the Faroe Islands are a bit further from continental Europe. Do they have a separate definition? So he contacted friends at the Danish Mapping Agency and asked them whether they could find out what the correct datum definition for the Faroe Islands should be, and could they find an authority for it. And they found a note written in pencil at the back of a drawer in a filing cabinet, and that was the root authority. Very many mapping agencies were not they're publicly owned bodies, but they were responsible only to themselves, and decisions they took were decisions which were absolute and final. And it wasn't terribly important what happened beyond that. Now, the next step that we find, which involves the author of, or the second author of this book, Roger Lott, was the creation of the European Petroleum Survey Group, because sea charts were taken in decimal degrees or in degrees, minutes and seconds, possibly decimal seconds. But nobody tried to say where the boundaries were between countries at sea. One knew where the countries were, and each country had a mapping authority with its own definition of the datums. But when you needed to divide up the North Sea using the median line or other legal definitions for where the boundaries between, say, Danish, Netherlands, German, UK, Norwegian, Faroe Islands jurisdictions were in the North Sea, you needed to be able to say how one datum in one country related to the datum in the other countries. And this led to the creation of the European Petroleum Survey Group. And they started with a spreadsheet database, and Proj and Goodall used CSV files to tabulate the information which the European Petroleum Survey Group had found for a series of different mapping standards. Some of the maps are projected, others are in geographical coordinates, so they're in planar coordinates or geographical coordinates. And the European Petroleum Survey Group attempted to establish what the legal authority was for each of the sets of definitions. There are now tens, hundreds of thousands of sets of definitions covering the whole world, in the same way that the the oil industry or the oil and gas industry covers the whole world. But the European Petroleum Survey Group started for internal purposes and to make it easier for the lawyers of, say, two oil companies to negotiate with each other and to negotiate with the concession giving authorities in different countries to find out where the actual boundaries went. Because you could strike lucky and find oil in a part of the North Sea which the UK didn't claim and Norway didn't claim. So it was a hole in between. Or you could find that that your strike was in a part of the North Sea which both the UK and Norway claimed to be within their median lines. That's not good either. So you wanted to have clarity about the authority for where to put the boundary. So the EPSG built up a list, and this is then looking at the EPSG list, asking it where one finds Oslo in any of these. This is the Norsk Geografisk Oppmåling from 1948 standard for Oslo, the representation which we find here. And this is these are the EPSG codes for these representations. The first one is in geographical coordinates. The others are in bands running vertically up Norway. So that if we look at the arguments for the first one, this is in geographical coordinates. It has a value for the major axis. It has the relative flattening at the poles. It has a prime meridian of Oslo. That's the stone outside the office of the surveying authority. However, with the changes which have occurred in the way in which things are represented, the way in which the datum is represented has gone away in the representation here. If I was doing this talk 2 years ago, 3 years ago, then we would have got an informal datum for the stone behind the surveyor's office. But look, we're in the 21st century. We have satellites, we have all of this kind of thing. And a stone behind an office in Oslo, when the stone was put there in the 1850s, the 1860s, this is not what we need. If we look at what we were being shown prior to the most recent Proj libraries, which are attempting to catch up with the fact that 1984 was 36 years ago, the coefficients needed to transform 7 coefficients, which were needed to transform to WGA84 from NGO 1948 Oslo. These are presumably there's some authority for it. However, we aren't getting when these are no longer being returned. The definition itself, the internal definition in the database, does contain the values which are needed. But what we need to find out is, say, if we wanted to get from the 1948 Norwegian geographical coordinates to contemporary geographical coordinates, looking this up in the European Petroleum Survey Group database at the moment, this is the operation which one would get, and one also gets a 3-meter accuracy coming from that one knows that the coefficients with the precision with which they're given, these here, the helmet, these values here, they will give us about a 3-meter precision from moving from an old map in the original geographical coordinates representation to WGS84. WGS84 is the 1984 standard, it's not the contemporary standard. So the representation of spatial data in all free and open source software, and indeed much of commercial software which was not developing its own systems for handling coordinate reference systems, depended on Proj, and up to and including Proj 5, which was released in 2017, one got these ad hoc transformation capabilities, so that you could move, say that you wanted to move from the Norwegian 1948 datum to the Danish, again, legacy datum. Then Proj would let you go to WGS 84 and then back out again to the other datum. This was fairly messy. One of the things we noticed was that I write here, everybody knew or should have known that each new release of the Proj and Gödel CSV metadata files could update transformation coefficients enough to shift the outcomes a little. An anecdote, the key data set used by Peter in his book on the foundations of GIS and by Edse Pebsma in the GSTAT package examples was from the Mersbank. And this was in a Netherlands coordinate reference system known as EPSG 28992. And each time a new version of the CSV files were issued, then we got the position shifting slightly. It might shift by a couple of centimeters or perhaps a little more, depending on what they were. So that when we got to the point at which we wished to display keyhole markup language files, that we're converting the points at which the soil samples were taken along a 3-kilometer stretch of the bank of the River Meuse near Maastricht, that they ended up somewhere else. The differences were not very big, but each time a new version of Proj and Gödel came out, then they shifted a little bit, because in this case we have 278.3. What I had pulled out previously was that. But if you got an extra number in the 0.37, say, or 0.33, and so on, so that for each of the numbers which were being used as coefficients, then you, as time went on, you got more precision. Nobody time-stamped the coordinates, and some geodeticists would wish to have each coordinate time-stamped, so we were guessing very much on where things should be placed in order to be placed adequately in the context of the time at which they were observed. So that, for instance, we know that US census tract boundaries should use the NAD 27 framework. And if you make a mistake and say, oh, no, it should be NAD 83, then they end up being slightly shifted in relation to the actual place where they should have run, so that you get boundaries appearing to run, once you get out to web mapping, appearing to run not down the middle of a river, but on one of the banks or further inland, and things like that. Does this matter for analysis? If you're analyzing a single data set, no, it's completely irrelevant. If you're trying to integrate two data sets which have exactly the same coordinate reference system, and you know that you can rely on that, again, makes no difference. The point at which you need to integrate data sets which use different coordinate reference systems, you need to convert between them. If both of them are using the same datum, again, you probably get off without too much trouble because it's just a mathematical operation. But at the point at which there are differences in the datum definitions, you need a system, an underlying system to allow you to integrate the data. So you could say that spatial data appears to be simple to handle, but it's much worse than time series in 2 dimensions. And with time, you also need to know whether you've had the leap seconds and which time zone you're in, and so on and so forth. Now, the way in which the SP package represents coordinate reference systems is as a proj string. However, in the last year we've made changes which supplement this. The representation in SF used to be an integer EPSG code and a proj string. Proj strings look like this, so that it's a simple string with very little markup, but the tags have a plus in front and equal sign behind. There are no spaces between the key and its value. So you've got a key value set up, which is fairly easy also for humans to write. The international standard at the moment is what's known as well-known text 2019. This is an example of well-known text 2019, and in proj this would look very, very different. Okay, so that I'm now going to describe where we are in terms of the status as things are at the moment. We found out that 1984 is not a good idea. Two of the geodeticists who have been working on modernizing proj, so making it fit for purpose in a situation where it was ceasing to be fit for purpose because the datum tag was not well authorized. The 2WGS84 tag wobbled as that it changed from time to time. The coefficients changed, and we didn't know which authorities were being used to change them. And also there were a number of informal data transformation grids, particularly in North America. So what they write in 3 years ago is fast forward 35 years since the WGS84 and the introduction of the proj4 library. Proj4 has now been changed just to proj to get away from the association with previous versions, classic proj4. It's used a lot, but geodetic accuracy is desirable simply in order to be able to adequately combine data which now has much higher accuracy than previously. So that if we're dealing with data in agriculture and construction, then plus or minus 150 meters is really not good enough. We don't need nanometer, but it'd be quite nice to know what the accuracy is. So a meter would be nice to know. So that moving away from pivoting through WGS84 became crucial. WGS84 is in a way, as Martin Desiro says, it's a distraction. Any hub transformation is always bad because you're moving from the source to the hub and then from the hub to the target, rather than moving directly from the source to the target, avoiding additional numerical error. So that this is a picture which shows a little of why things are happening. These are definitions for South America, of how South America itself is moving, taken on 3. This is in the early 2000s. This is about 10 years ago, and this is 3 years ago. for how one is looking at the movements of the continent itself. And you can see in the zones where there are more earthquakes, then the movement of parts of the continent is stronger. And the length of the line here is in 20 millimeters per year. So that we're from a situation previously where we really had no way of observing these movements. And the lines, of course, are the tectonic plates, or the assumed boundaries of the tectonic plates. So and I'll carry on talking just in case the Zoom sharing breaks down again. So I'm not sure why I couldn't turn it off previously. So I'll carry on until 10:30. So changes began to occur in Proj from 2017, and the Proj string, from having been something which was everybody's friend and most people could grasp how a definition worked, we're now in a new world where we are obliged to use not only well-known text 2 of 2019, and I'll see if I can open this page, and this may then bring everything down. No, that worked okay. From Proj 7, which appeared in March this year, we now also have access to an on-demand content delivery network for hosted by Amazon for delivering cloud-optimized GeoTIFF data sets, giving the grids for particular jurisdictions. Not all are yet, so not all mapping agencies have woken up to the fact that it's helpful to have something else going on, so that if, say, we go to the Gulf of Bothnia and see what's going on there, this is a place where quite a lot happens, and there are the Finnish mapping agency has released a fair number of grids for expressing the way in which the what's it's called, the geoid undulation is occurring in these areas, and about 21 meters in this situation. If we go to Norway, then here we have the east velocity, the north velocity, and the up velocity. You can see that the east velocity is that this part of the fairly old crust is moving westwards at about 1 millimeter a year. It's moving northwards at about 0.1 millimeter a year, but it's moving upwards at about 2 millimeters a year. And these realignment grids are now attempting to be brought into the way in which transformation pipelines work. So that the idea is to incorporate the best, or to attempt to establish the best possible transformation pathway to go from one coordinate reference system, source coordinate reference system, to a target coordinate reference system. Now, a glance back again. In both S and R, use was made of code originally written by in the MapProj package, code originally written by one of the authors of Unix and Plan 9, who wrote the code because he flew his own plane. Among other things, he flew from the US to Tromsø in the early 1990s, navigating using his own software. I mean, if you're a software nerd, that's the kind of thing, I guess, that you do. However, the underlying assumption in that software, and it's hardwired in a particular header in the source code, is that the eccentricity of the Earth is defined in this way. And the eccentricity is the major ellipse squared minus the minor ellipse squared divided by the square of the major ellipse. That's the eccentricity. And it turned out that all of the MapProj package uses the Clark 1866 ellipsoid. So we can establish that this is what's going on. This is the definition in the file. And if we then use the formula for calculating the eccentricity from I live and lot, then we can work it out from the list of from the Proj list for the Clark ellipsoid. So that here we've got the Clark major and L, and yeah, definitely the MapProj package is just using that ellipsoid. It's not using datums at all. We adopted very early on Proj for representing the coordinate reference systems for spatial objects. This was introduced in the SP package, and it was followed through in raster and the SF package. Now, from Proj 6, then the CSV files have been dropped, and one now uses an SQLite database file, which is updated each time Proj is released to the current version from EPSG. The current release in Proj 7.2 is from EPSG series 10, which is new and changed some of the details. Now, if we use our SQLite to have a look inside and see where it is, we can find out in SF where these files live. That's where Proj gets its data from. Google gets its data now from exactly the same Proj SQLite database. So, connecting to the database, we can ask it to give us a list of the tables in the database. We won't go into what's in them, but you can see that there are very many of them, and they include the geodetic coordinate reference systems, the coordinate operation methods, the conversion methods, so that authority to authority preference, so that if one has a set of coordinates in a part of the world where there are multiple authorities, then one can say, well, actually, I prefer the local Greenland to the Canadian for finding which set of parameters should be used for sea areas between Canada and Greenland, or that kind of thing. There are not very many people doing that, but we then have the whole. So that there's far more detail here than anyone thought was present. The way in which things were handled previously was that we had the Proj string key value form, and as I've already mentioned, up until about 5 years ago, we stressed the need for accurate coordinate transformation simply because if you want to integrate data from different sources, then otherwise you get mismatches. So that if you're looking at sort of putting crime incident data, which is point data, on census tracts, then you don't want to have the problem that you're getting you're not getting them correctly registered. However, web mapping has made things more complicated with the leaflet package, MapView and TMap, and other packages, Mapbox and so on. All of these permit us to put data onto a web map background and then to zoom in, because when we can zoom in, we can see where the possible infelicities are present, so that things which you couldn't see by just plotting to screen suddenly jump into prominence. They're things that you now can see very directly. Web mapping, the way web mapping functions is to transform input objects from whatever their representation is to OGC CRS84, which is a geographical WGS84, which is then further transferred to EPSG 3857, which is a pseudo Mercator projection on WGS84, or in some circumstances on the sphere. And this is carried out internally before it gets to the web mapping. So that MapView uses Leaflet to expose the mapping data on this basis. But if say that you have data which is in the standard of a European country, or is UTM zone 33, which is typical for 32, which is typical for Norway, then in order to be able to display it on a web map, then you need to, or the software itself carries out two sets of transformations. First to the 1984 coordinate reference system, and then on to the pseudo Mercator for display. Google Maps is now able to display something which looks like a sphere, and this I think is in S2, but it could be in some other system, as I haven't looked. What happens in MapView and TMap is that any input is coerced to stars, raster, SF, SP, and so on, and then ST transform in the SF package is used to transform to the standard geographical coordinates in the WGS94 to WGS84 in order to be displayed. One of the reasons for writing not EPSG 4326, which is what has been done until recently, is because this by definition has latitude in front of longitude, so it swaps axes in relation to what we would expect for visualization. For visualization and plotting, we'd expect the X coordinate to come first and the Y coordinate to come second. But in EPSG 4326, if it's followed strictly, they're the other way around. You get Y and X. Now, looking at the John Snow data that we were looking at yesterday, we face the question, where is the Broad Street pump? Now, the Broad Street pump is in Broad Street for obvious reasons. However, if we read in, and the geo package is now part of the SF geo package, part of the SF package, and has been since earlier this year, because it was convenient to have a painful and so wake up example readily accessible. So if we read this in, it's the way the data are currently constructed. We get a report back that this says that this is transverse Mercator. This is a standard Ordnance Survey of Great Britain representation. Transverse Mercator is the projection which is typically used. Its EPSG code is 27700. It's a bit like remembering telephone numbers. Early in 2020, so that subsequent to the talk that I gave in this edition, in the previous edition of the course, we rolled out the changes which needed to be made. Prior to that, the Proj4 string representation suffered degradation when using newer versions of Google and Proj. So that what was happening was that if we fed in to from Proj4 and Proj versions 4 and 5, if we fed in a previously acceptable definition of the OSGB projection, standard projection, transverse Mercator, standard parameters here for the latitude of origin and the longitude of origin. But we had the plus datum OSGB 36, which was in the original not authorized CSV files. This definition as such is no longer accessible from a proj4 string. So that here what we're doing is converting this to legacy. We're then saying, okay, so we want the proj4 string from this, and then we're taking the string representations after this has been ingested to see what are the differences between the so which has been dropped from this one in relation to this one. So this is after we've processed the proj4 string, and the difference between them is that this is missing in the proj6 representation. It was in proj5, it's no longer in proj6. What has appeared in the proj6 representation in relation to the proj5 is that it says, okay, I don't know what the datum is, but the datum definition is telling me that the ellipsoid is airy, which is one of the known ellipsoid definitions. And this means that we're going to be out by about 125 meters. So that emulating what was happening from the late spring of 2019, when Goodle 3 appeared using proj6, is that we were seeing the kinds of definitions which were problems which I'll demonstrate in just a moment. So what we're doing here is to corrupt the definition, the one which we've read in from file, because I'm using the current releases of SF and current Proj and Goodle, so that they have now repaired and we've rolled out the repair. But prior to that, if we had not undertaken steps to change things, then we would have had this situation here where putting the legacy representation into this. So that we're then saying, okay, so we will convert from the planar coordinates in the OSGB projection, transverse Mercator, airy, OSGB datum, and so on, to WGS84. So we're making the transformations apparently identical, but if we measure the distance between them, we find the distance is 125 meters. We can examine this by looking at them on a web map. Oops, we didn't want to zoom in, we wanted to zoom out. This is the WKT2 2019 representation, WKT2 2019 representation, and it's in the same position that we had with proj4 previously, which seems perverse that we actually have to run to stay at the same place. But with the change in the external software, this was the degraded placing, so that we would have to say, okay, so the pump is no longer in Broad Street, Broadwick Street as it's known by OpenStreetMap. It's in Industry Place. This is 125 meters as the crow flies. The Broad Street pump really is here. That's where it is. So that's the reason for changes which have occurred. So that if you refer to any earlier descriptions of how coordinate reference systems are handled in spatial data in R, then you need to be aware of the fact that there have been very recent changes during this year. So the resolutions which we've implemented are to introduced WKT2 of 2019. This is the version that we've adopted. Almost everything works under the hood, so that you won't observe any changes, even using packages which have not yet been updated. We have conducted an extended campaign of repeat checking about once 3 or 4 times a month, sometimes daily when things were changing rapidly, running reverse dependency checks. That means that on my server on my desk, I change SP, Argoodle, SF, raster, and then run their reverse dependency checks, many of which overlaps, that we only need to run them once, on a little over 900 packages which use their facilities, and check to see whether things are broken. Some of the breakages were because of issues in the other packages. From a maximum of around 50 to 60 serious breakages, other things which were not being tested for, which were not being used in examples, didn't lead to breakages, but may still lead to difficulties. We were not able to trap them. But for packages which were properly written and checked to see that the projections still worked, then we found 50 to 60 which had breakages. We contacted their maintainers, and most recently in August, I bulk converted the stored data objects in 115 packages and proposed them to the package maintainers, so that at their next update, they should update the package to have the modern representation of the coordinate reference systems included in their stored objects, which very often they were using for running examples. Probably not all of them have been captured, and certainly some of the ones storing raster packages won't have been captured. But we hope that we've removed most of the proj4 strings from packages on CRAN. Scripts and examples and other particularly blog posts explaining how you should handle spatial data may not have caught up with this. A minor point, which I've already mentioned, is to do with axis order, and this is something that we feel that we do not have control of yet. SP and Argoodle attempt to enforce in all circumstances what's known as visualization or GIS order, which means that eastings and X are always first, and northings and Ys are always second. This was something we imposed on SP initially, and we're still attempting to make sure that this stays the same. However, in SF, you will see situations in which a lookup to EPSG 4326 leads to north being the first coordinate and east being the second coordinate, so that this is Y first and X second. SF will still treat the coordinates as X first, Y second, but the representation says that it's the other way around, and we don't know what the consequences are for saving the data. For the SP workflows, of which there are far more packages which depend on SP than SF, because SF is much more modern. Then we managed to switch so that we now get the proper name of the coordinate reference system as being WGS84 with axis order normalized for visualization, even though we said we wanted EPSG 4326. The name which is given here is WGS84, so straight out, but in this one it's WGS84 with axis order normalized for visualization, which is a possible reason for difficulty. So that if say we look at the the transfer of data, so that if you're transferring data which is in the SP representation to the SF representation, and just look at that segment of the output, then the axis order as it was in SP. So the coercions going that way work, and the coercion going the other way works, but we're not confident that we have adequate control. One resolution which was suggested, among other things, by Evan Rowan, who's the key person writing most of the changes in Proj and Gödel with regard to coordinate reference systems, was rather to use this representation. The OGC is the Open Geospatial Consortium, which has most of the companies involved, because it's the representation used by GeoJSON, which also mandates eastings before northings. So this is a more secure, because both in SF and in SP, then you get east before north in both cases. And the difference, the only difference being that there's a textual difference here, because rGoodle and SP are extracting the representation directly from Proj, and SF is extracting it from Proj through Gödel. So this is the way that Gödel represents it, so that the Proj representation also reports the scope, which is the temporal area of relevance, and the area. However, the box is always reported with northings first, so that this is south, west, north, east, for reasons which nobody understands. So that these are the way the current status, so that rGoodle, since very recently, has preferred to use Proj for instantiating the coordinate reference systems objects, but it's possible to use Gödel to go through the same route. Then when one is not using Proj, then the text values are the same. If we go the other way, then the text representation is not going to be exactly the same. But if we use comparison representations, then they're not strictly equal. That is, there is small textual difference between them, but they are equivalent, which means that they're saying the same thing, that the same representation, and they're also equivalent apart from axis order. There's also a tweet to which I'll draw your attention. I shouldn't have done that, but so I will now have to back out of this, go back to this, and create this as a separate. So that there's a tweet linked from the slide, which is fairly recent. This was 2 weeks ago, where Barry Rowlingson is asking what's going on with this confusion, and if you follow the link, then you can find the further discussion, which it turned out to be that Gödel treats things somewhat differently from Gödel treats the way in which you write the representation somewhat differently from just Proj, even though Gödel is sitting on top of Proj. So that the coordinate operations, this is now rounding off, coordinate operations can also be managed, as you could possibly see from this, so that when one is looking at a source or target coordinate reference system, one is also interested in where in the world this is in order to try to find a suitable pathway. So that what we're trying to do is to find a subset of all of the possible pathways for transforming between source and target by using the geographical extent of the area of interest in order to find the data. So that in order to get from the OSGB coordinate reference system to EPSG 4326, 4326, we can do this without specifying the area of interest, or we can take the bounding box, expanding the bounding box around the pump in geographical coordinates. And we got 9 candidate operations found when the string contains datum information. 8 of them can be instantiated, 1 needs a grid. But 4 of those, we go down to 5 if we use an area of interest, so that the lookup time in the database drops if an area of interest is used. In SF, the area of interest is not fully implemented. In RGoodle, this is for the SP transform operation. If it is possible to run it, then it is run first, so that SP transform simply uses the area of interest directly. So, and also SP transform silently records the last used coordinate operation, which was found by SP transform, so that it stores it in a package specific environment. And this can then be reaccessed, so that if one needs to use exactly the same coordinate operation, then this is retrievable. And the operation which is found, which was used here to give us the representation that we could see on the web map there, was using a Helmut transfer 7 coefficient transformation, which was giving us then fairly adequate 2 meter accuracy. If we look at the transformation pipeline, which only deals where the datum definition had been dropped, this doesn't contain any steps. So this step here is missed, so that we go straight from inverse transformation of the transverse inverse projection of the transverse Mercator. That's all the same. That's all the same. And then we're going on here. We get to Airy. Okay, so that we're not pushing the vertical transformation. So that we're going through here. So that this element is absent, and that's why we get the 125 meter shift in from Broad Street to Ingestre Place. And also when we're looking for, when we're using the degraded representation, we only have one operation, and that's that has what's known as ballpark accuracy, which is that nothing in the database knows how accurate that is. So all it's saying is that we don't know. Now, just to round off, there's also the possibility to use the content download network, and in this case, it is possible to transform using a publicly available so open access published Ordnance Survey of Great Britain grid for making the horizontal grid shift, so that this step here is inserted instead of the Helmut transformation, and this then gives us single meter accuracy. And this is the idea that being able to use the content distribution network, content download network, by default in rGoodle and using Proj 7, it's turned off, but it can be turned on using this. And then if a grid is available, the grid will be downloaded and stored in a directory, which either will be in your home directory in a standard place, or in this case, I put it in a temporary directory because when the rGoodle package is being checked on CRAN, it cannot overwrite the running user. So it can only store things in temporary directories. Okay, so what was happening here? So this is the directory where the downloaded grids are going to be filed. If I say list files in that temporary directory where I'm putting the files. So I've created a directory with this name in R's temporary directory, and there are no files there. There are no files there. However, once I've run the operation, as I can say, well, what's in the temporary directory now? And in the temporary directory now is a file called cached.db. And how big is it? It's 320 kilobytes. So it's not very big, but it was downloaded on the fly. And because it's now in that directory, if I want to do further operations, then there's no further cost for downloading the downloading the grid. So that downloading the grid on the fly is seen as being much better for most users, because downloading all of the published grids for the whole world, which is now weighs in at about 600 megabytes, probably isn't necessary, because most people are only working on particular parts of the world, or if one's working on global data, one doesn't need detailed transformation grids for specific parts of the US or specific parts of Luxembourg or whatever. So, okay, so what's the distance now between the point that we've reached? This is the gridded one is with G. This is the distance to the degraded location. It's again 125 meters. That's what we knew before. The distance from the previously attainable, it's the Helmut transformation location, and the grid transformation location is a little under 2 meters. And if we put this coordinate up on the web map, which I won't do, you can see that it is actually where the pump is, so that it is more accurate. A final point is that we could make the same measurements using the S2 package, and we see that again it was about 125 meters and 1.7 between the others, so that the S2 package gives us more or less the same distance as using spherical geometry in another way. But those are this is where we are in terms of coordinate reference system representations. So the status now is that we feel that we're more or less in a position to claim that the consequences have now been addressed. We have no control whatsoever over scripts running workflows in government labs worldwide. We know that the packages are used extensively in US government labs, in the EPA and places like that. So we hope that we've been able to make changes under the hood which allow people's workflows to continue working in the way that they did without suffering the degradation that we saw by not taking account of the changes in Proj, so that we hope that things are okay. There are still signs on the mailing list and on Twitter that users who are obviously not looking at what's going on under the hood haven't realized that we've switched their vehicles from diesel to electric. And if you're driving an automatic car, then probably you don't know that you're now in an electric car rather than being in a diesel car. But diesel's going out of fashion, so we've done the work for you. We've taken everybody's diesel cars and put electric engines in them and batteries and stuff. When you run out of battery, you'll probably realize that something has changed, because putting diesel into a battery doesn't help. So when people are trying to create new objects using Proj4 strings, then they may run into difficulties. And some understanding of the fact that changes have occurred under the hood will now be essential. It's tiresome. It's taken a lot of work, but we feel that we're more or less there. At the moment in SF workflows, the warnings, there are very few warnings given to alert people to changes. In SP and Argoodle and raster workflows, there are lots and lots of warnings, but when SP 1.5 and Argoodle 1.6 are released, which we hope to do either later this year or earlier next year, then the warnings will be turned off by default, but they can be turned on again for labs and other uses where one still needs to be warned that something in the representation one was using has now gone away. An open question is how to handle the reproducibility of older results. But this has always been something of a problem, because the coefficients of the helmet and other transformations have also shifted over time depending on the versions of the EPSG database which have been packaged with Goodle and Goodle and Proj. So I'll now attempt to stop the share, and this time it worked. I will stop the recording.